To end class yesterday, we talked about there were 4 reasons that domain has to be restricted. Okay, 2 of them, logarithms and trig functions, we're really not going to run across right now. But the other 2 we are going to run across. And the first is the x causes division by 0, which is not a thing that we can do. Or it puts an x causes a negative under an even root, right? You can't take the square root. You can take the square root of a negative number, but you don't get a real answer. When we talk about domain, and later we'll talk about range, we're talking about what real numbers, right? What real numbers versus imaginary numbers. So as we look at this warm-up here, for the first one we have y equals 1 over x minus 2. And with this, we're going to go ahead and look, I mean, there's no even roots, right? That's not an issue, but there's a denominator with an x in it. So as I look, if I put a 2 in here, it fails, right? If you do 1 divided by 0, it's not going to work. So here's the domain for this one. I'm just going to go ahead and write it using inequalities, and then we're going to just review inequality or interval notation here real quick. I'll come back and look at it. So here our domain would be that x is not equal to 2. Whenever you say not equal to, you're implying it is equal to everything else, right? So everything except 2. The next one, f of x equals the square root of x plus 5. As soon as I see a square root, I'm thinking, hey, there could be a domain issue here, right? So I can take the square root of 0. It's just 0. And we can take the square root of any positive number. Right? It might not be a pleasant answer, but it will be an answer, right? Domain's all about getting an answer, not about getting an answer you like. So here, I would solve the inequality that x plus 5 needs to be greater than or equal to 0. Subtract 5 from each side, we get x is greater than or equal to negative 5. It's not a bad idea to think about if I put a negative 5 in here. Okay, I get 0. I can do the square root of 0. If I put negative 4 in here, which this looks like it's in the domain, I get 1, which I can take the square root of 1. So we do that. So here, for this one, we would say the domain is that x is greater than or equal to negative 5. Again, we'll come back and look at intervals if you did it that way. For this next one here, C, where this one, hopefully A jumped right out at you that 2 is going to be a problem. Here it's not as obvious, but what we want to do here is, since we have a quadratic, we want to go ahead and factor it. So with this, we have x, and then you have x minus 4, x minus 3. Okay, so as we look, if we put 4 in here, we just divide it by 0. We don't want to do that. If we put 3 in here, we don't want to do that. So for this domain, probably the easiest way to write this is to say x cannot equal 4, and then x cannot equal 3. So we're excluding these 2 numbers. That's implying that it could be any other number, and we're going to get some sort of answer. Right now, you might, I don't know, someone might look and be like, well, what about 0? That's a good question. Because if you put 0 in here, you do get a 0 in the numerator, but you still get a 12 on bottom. Can we do 0 divided by 12? Sure, it's just 0, right? That's defined. It would be the 12 divided by 0, which would be undefined. Okay, so here is just a recap of some of the tools, things that we use with interval notation. It should be something you've been exposed to before. So with this, remember, we're going to have these intervals that kind of look like ordered pairs sometimes if you're not careful. But a parentheses will mean that there's an open endpoint. So if I have an interval that goes from negative infinity to 2, and I have parentheses on both sides, it means it goes all the way to the left forever, right? Every negative number ever. And we'll talk about that later. Infinities or negative infinities always get parentheses. Infinity is not a number, it's just a concept, right? If infinity was a number, then we could write a bigger number. We could just do infinity plus 1, or infinity times infinity, or whatever. So for this one, this is an open endpoint. It means that the 2 is not included in this interval, but every number up to 2 is included. So it's open. you can't name what that biggest number is. All you know is that it's a little bit less than 2. Right? If you tried to get close, you couldn't get there. If you're having trouble with these at all, I would recommend kind of thinking about what they would look like on a number line. Just a very simple number line, right? Is it would be everything to the left of 2, but not including 2. That's what that would indicate. So that would be like a true inequality symbol. If we wrote that as an inequality, that would be x is less than 2. Okay? Whenever we write inequalities, we don't put the infinity. Like that's just an interval thing. It's not an inequality thing. Okay, so brackets mean closed endpoints, means the endpoints included. Whenever you're writing these different intervals, you always put the smaller number on the left. Always, right? We do use negative infinities and positive infinities. They always get parentheses. If 2 or more intervals, you know, because like a lot of these that we're going to look at here, even A right here, you're going to have 2 intervals. You connect them with a union symbol. It's just like a U without the leg. It means or. So it's in this interval or it's in this interval. This symbol I use a bunch. This is like a C and an E kind of crossed. So again, it's like like that. It's just a math notation. It just means is contained in or is an element of. So it's saying that X is going to be in this set or this union of sets. It's a math symbol that comes up. And a quick way to write all real numbers. So say you have a parabola, right? And the domain's all real numbers. No big deal. You could use this R right here, which is just an R with like a double vertical stick. That just means the set of all real numbers. So a lot of times you'll write things like X is contained in the set of reals. That's just a way to say the domain is all real numbers. Or that's the same as saying negative infinity to positive infinity. It's the same thing, different way of writing. So knowing that, let's go back to our warm-up here. And we have, for these domains that are already listed, now it can be helpful when you're going from one to the other to make a number line, but you might not need to. So here, this domain is everything except 2. So if I think of that as a number line, at 2 there's going to be an open circle. We're going to shade to the right, and we're going to shade to the left. Okay. Now, in terms of the interval notation, we want to start as far left as possible, which that would be all the way over here at negative infinity, correct? Yeah. So we're going to say negative, and I could say X is contained in if I wanted to. You don't need to. It's just something nice to make sure you're with the right variable. It does point out that it's not ordered pairs, though. It's like, hey, we're using set notation here. But negative infinity, the next thing I come up to is the 2. Now, 2 is not included, so that would be a parenthesis. And make sure your parentheses are parentheses and your brackets are brackets, and you don't get some sort of weird crossover symbol that counts for both. And then union, parenthesis to infinity. Right? So that's what it would look like in interval notation. So this inequality is the same as this number line, is the same as this interval line. Okay. If you want to, maybe take a second and try to write intervals for those next 2. Okay, so for part B here, we said the domain is X is greater than or equal to 5. Now, I know greater than or equal to means I'm going to do a bracket as opposed to a parenthesis. But if we do the number line to kind of get us from one to the other, that's a closed circle at negative 5. X is greater than or equal to. So it looks like that. So in terms of our interval notation, we're going to say bracket, negative 5, comma, infinity, parenthesis. That's what we would get there. All right? Are we good? For this next one, in terms, if you're missing these and you're not drawing the number line, I might suggest that you draw the number line. So here, these are both open, shade between, shade to the right, shade to the left. Again, this is not a simple interval. It's kind of annoying to write this one. And our domain, get all fancy, X is contained in, I'm going to start from the left again, So parenthesis negative infinity, and then 3, but that was open, so I put a parenthesis there. If it helps too, I think of an open circle. If you cut it in half, you get a pair of parentheses, sort of. Right? A parenthesis half a circle, or an arc of a circle. Union, and then 3 to 4, and then union 4 to infinity. You'd want to have a union symbol between each interval, right? Because it means or. So it's either between negative infinity and 3, or it's between 3 and 4, or it's between 4 and infinity. Again, intervals are much easier to write, right, by far. But sometimes we need to, or I'm sorry, inequalities are easier. Intervals can be a pain. Okay, so the next thing we want to talk about is our range of our function. Okay, we're domain. We had a nice little list of 4 things to look for, right? We talked about on the last video, or we kind of talked about in the review there. Range is not that simple. Range can be all over the place, some really kind of challenging questions. You got to consider lots of things. So we're just going to look at how to look at the graph and determine what our range of our function is. So remember, it's the set of all outputs for a function. So when you consider the domain, that's all the inputs. Each of those is going to give you an answer. You're going to see what those answers are. That's going to make up your range. So we can still use interval notation. We can still use inequalities. The variable will usually be y, or I guess it could be f of x if you had it like that. But really what you want to do here is on these graphs is you just want to look at it and imagine to find the range, just compress the graph onto the y-axis. Right? If there's points on it, it's in the range. If it's open, it's not in the range. So let's go ahead then and we have these 3 equations here. Let's use our calculator to get a good graph and then try to figure out what the domain and range would be. Now actually, it would be a better exercise to go through all 3 of these and figure out what the domain is before you type anything in your calculator and then investigate the range. So let's take a few minutes and do that. So let's take these 3 functions, y equals x squared minus 17x plus 30, y equals 14 over x minus 5, and y equals x cubed plus 6x plus 7. See what we can get for their domain and range and make sure we can get a good graph of those. Okay, so for these 3 examples, we're just finding the domain and range. Remember, that's just the domain is just what x's will work, will give me an answer. That's all. And then the range is what kind of answers do I get? Right, when there you got to look at your graph. So for this first one, it's y equals x squared minus 17x plus 30. D for domain there. So the domain is, I'm thinking about my checklist. Are there any even roots here? No. Are there any fractions or x's on bottom?
No.
No. My domain is all real numbers, so I'm going to say x is contained in the set of real numbers. That's the answer. Or if you didn't want to write it that way, you could say negative infinity to positive infinity. Or you could say x is real. That's it. That's all they have to do for the domain there. Okay? Now, the range, hopefully we know this is a parabola, correct?
Yes.
And it opens up. So the range is going to be restricted because there's some, like if I'm the parabola, there's some y values down here that don't get used. So when you graph this, what I wanted you to see is when you graph it on your calculator, you should get something that looks kind of like that. Okay? There is a low point, correct? Now in terms of range, remember, I like to think of taking all the points and just pushing them over onto the y-axis. And then it's going to be like a vertical number line, right? All filled in. So I went ahead and when I graphed this, and I know some of you did, hopefully you used the minimum command to figure out where the vertex was at. And when you do that, you get that this point will be 8.5, negative 42.25 on your graphing calculator. You have to adjust the window a little bit. A 10 by 10 won't work. If you didn't get that, you should go back and try it sometime because that's how we're going to get our skills to improve. But as I look, if I squish all the values over here, the lowest y value is going to be this negative 42.25, correct? So the range would be y is contained from negative 42.25. Are all these points above it going to get filled in?
Yeah.
To infinity. That would be the range. Okay, so that's the domain, that's the range. Did we have to use the graph at all for the domain?
No.
No, we didn't have to. We good there?
Yes.
Okay, for our next one here, we have y equals 14 over x minus 5. Now, right away, hopefully, we're saying, hey, I bet 5's a problem here because there is an x in the denominator. There is going to be a domain restriction. So for my domain, I'm going to say x is contained from negative infinity to negative 5, union negative 5 to infinity. Would be one way to write it. Or you could say x is not equal to 5, which is a much easier way to write it, right? So we have our interval notation, we have our inequality. I didn't have to graph anything. Now, when I do go to graph this, did you guys graph it?
It's like a straight line.
Well, on your calculator, it's going to be a graph that looks like, out here at 5, it's going to look like this. And this. What's going on here is this is 5 right here on your graph. There's a vertical asymptote, right? Pretty much a lot of times if you're leaving a number out of the domain, you're going to have a vertical asymptote, which you should recall that. That means the curve's going to get as close as it can to it, but never quite reach it. If you go to your calculator and you have this graph pulled up and you hit trace, if you type in 5 for the x value, and hit enter, it'll give you just a blank for y. It's telling you like, I don't know. Now you could try like 5.001, it's going to give you a really big number for y. If you try like 4.99, it's going to give you a really small number for y. Okay, I was just corrected, that was a positive 5. I don't know where that came from, but 5 is the problem, right? So, now with this range here, as you look at it, you see this just goes out forever and this goes out forever. It's kind of tough, but as you look at the graph, we got to kind of figure out, if you keep going to the right forever, do you see this is going to keep getting really, really close to 0, but it doesn't seem like it's ever going to get there? Same thing over here, it's negative. It doesn't seem like it's ever going to get there. Yeah. If we look at the equation, that will kind of make sense, because the top is 14, correct? Which is just a constant. Is there any number I can divide 14 by that will give me 0? 14 divided by 14 is 1. 14 divided by 0 is undefined. There is no number you can divide 14 by that will give you 0. Ever. So, that tells us here is that x cannot, or this is range, so y cannot equal 0. That's why we have to look at the graph and get an idea of the pattern there. Later we'll talk about rules for finding asymptotes and how to graph these. We're just kind of reviewing domain and range for now. So if you didn't know how to graph this by hand, that's okay. We're going to get to that. But if we wrote it in interval notation, it would be negative infinity to 0 with a parenthesis, union 0 to infinity. Okay? Now, this last one. Kind of a trick question, see if you're paying attention. This is a cubic, right? So, are there any domain issues here? No, there's no division. There's no even roots. There's nothing. So, our domain is that x is contained in the set of real numbers, or negative infinity to positive infinity, or x is real, or whatever you want to write it. Now, for our range, when you graph this, it's kind of nondescript, right? It just looks like, kind of like that, I think. Very kind of boring. Well, we should know that if it's a cubic polynomial, which this is, that one end goes up and one end goes down, correct? It's the even ones that have the same ends, like a parabola. Cubics look like this. So, what do you think our range is going to be?
Y, E, R.
It's going to be all real numbers, right? So we can say y is contained. We do not say y-e-r. That is not a, that's a symbol. It's a, yeah, that's like, no, so y is contained in the set of real numbers. You could have said, though, if you hate that, you could have said x is contained from negative infinity to infinity, and y is contained from negative infinity to infinity. That would work also. Okay, we want to talk about when functions are continuous and when they're not. I don't have a great definition for what makes it continuous, but I think as we look at it, it's going to make sense. And the biggest thing I think of, if you can start all the way to the left and draw it without picking up your pencil, it's continuous. There's no holes in it. There's no vertical asymptotes. There's no jumps. Okay, so a function is continuous if we can draw it without picking up our pencil. Okay, so there's no holes, there's no jumps, there's no vertical asymptotes. Okay, so that's a continuous function. Every parabola you've ever drawn is a continuous function. Every cubic, every line you've ever drawn, they should be continuous functions. Okay, so, like an example of a continuous function would just be like our kind of just generic curve, right? No holes, no jumps. I start at one end. We're all set. So that's continuous for all x. Right? So sometimes you may look at a function and say, well, it's continuous on this interval and not continuous other places. That's kind of looking forward. For now, that's continuous. So it's easier to understand continuity when you figure out what's not continuous. Okay? And there's kind of three types of discontinuities that we want to look at. Okay? The first, and the most probably interesting, would be a removable discontinuity, and you can see this is on your paper there, or if you're watching the video, it's linked on the agenda. And that would be where you have just a typical looking curve that has a hole in it. Okay. There's just an undefined point. Right? So in this case would be a removable discontinuity. We can see that when x is equal to a, there's just an open circle. That indicates there's a break. Yes, I know that if you do the circle real fancy, you can draw, but there's a break. It's not continuous. Okay. You could also see one just like that, or similar to it, even if it's a case where it's open, and it may even be defined at that value. Like here, I have a point that's just off there. It's a piecewise function, right? So I have this function, there's a hole in it. Maybe there's a point with the same x value that somewhere else, but it's still a removable discontinuity. The reason we call them removable is if they can be fixed, not that there's anything wrong with them, but if they can be made continuous with one point. Right? So both of these, if I just took one point and stuck it right here, it would be continuous now, correct? If I filled in the hole. If I got rid of this point and put the point there instead, it would be continuous. That's called a removable discontinuity. As we look at more and more types of functions, especially as you get into calculus, we can work with removable discontinuities. They're kind of easy to deal with. The two that are not, the first is called a jump discontinuity. And that would look like you just have a jump. It's generally a piecewise function. There's a big old gap there. Is one point going to fix it?
No.
No. So it's called a jump discontinuity. It just can't be fixed. The other type that we see is a infinite discontinuity. And we just looked at one of those here earlier on the warm-up. Okay, so for an infinite discontinuity, what you're going to do is that you're going to have a vertical asymptote. Okay, when you have that vertical asymptote, it's going to make either the function is going to go up as it approaches the asymptote, or it's going to go down. Now both sides could do the same thing. So let's say before we had one that looked like this, kind of a typical hyperbola. This would be an infinite discontinuity, right? The function's only undefined at one point, but you can't put one point there to fix it, right? It's not repairable. It's not removable. And it even can occur and a lot of times if you get an inverse squared function, it might look like this. Even though both of these are going up forever, and they're just going to keep getting closer and closer on either side of that vertical asymptote, it's still an infinite discontinuity. It still can't be repaired with one point, right? It's not removable. It's an infinite discontinuity. So whenever you see that you're going to have a vertical asymptote, we're going to have an infinite discontinuity, right? If you have a piecewise function with a jump, you have a jump discontinuity. If you have removable, that's good to know. There are some other types that you might run across in calculus where the function just kind of goes crazy and you get all kinds of weird behavior. Okay, so for our first example, we're going to identify the type and the location of any discontinuity. It will also sketch a graph of it. I don't expect you to be able to graph this by hand at this point, but we can identify the discontinuities and things. So, as I look at this, right away, anytime I look at a function, I want to think about the domain. So as I look at this right away, can I see there's going to be a domain restriction? Sure. I'm just going to make a note of that. The domain is that x cannot equal 3. That's a problem. Now, there's no guarantee that that's what type of discontinuity that's going to be, but it is something we want to be aware of. Now, as I look at this function, do you see that these numerator factors? Yeah. Right, so we get x plus 3, x minus 3 over x minus 3. Well, if you notice here, we have a matching factor on top and bottom. Okay, so if we get a matching factor, we actually can simplify this equation. So we're going to simplify it, and we're going to write it as f of x equals x plus 3, but this domain restriction still applies. So we're going to say f of x equals x plus 3, x cannot equal 3. Because the original domain restriction still holds. Because if we go back to this original and we put 3 in there, we're going to get 0 divided by 0. Which is undefined, but it's a special type of undefined called a indeterminate form, which do a lot more with that in calculus. We do with limits and stuff. But it just means that something weird's happening there. So what will happen here is this graph will actually just look like you'll have a y-intercept here, so we're going to get, that's just the line x plus 3. And then at 3, we have an open circle. It's undefined at that point. So this would be a removable discontinuity at x equals 3. Now, if you needed to figure out what that exact point was, could you just plug 3 back into this equation? Yes. The line, so it's at the point 3, 6 is where that removable discontinuity is at. Okay, so again, you'll see there's going to be a removable discontinuity when you have these matching factors on top and bottom. So when you see that, you want to think removable discontinuity. Okay, for our second example, we have f of x equals x plus 1 over x squared minus 2x plus 1. I do have a denominator, so I need to factor it to see when it's equal to 0. There's a good chance it could cancel out again. So let's see. As we factor this, we get x plus 1. The bottom is x minus 1 squared. So as we look, there is no common factor here, right, between top and bottom. So in terms of our domain, we'd get x cannot equal 1, right? Because if it equals 1, we just divide it by 0, which is not something that we can do. So then at this point, we could go ahead and graph it and try to determine what type of discontinuity we have. Okay, if you graph this, I know that at 1, so if you get a denominator like this that doesn't cancel, so it doesn't cancel, then it's going to be vertical asymptote, right? And as you probably are not surprised, if you have a vertical asymptote, we're going to have a removable discontinuity. I believe the graph looks something like this. And now it might, I think it does cross the x-axis. This is not a great graph, but it's going to look something like this. Do we see that this is an infinite discontinuity?
Yes.
Right, because we hit that vertical asymptote, right? That's called an infinite discontinuity. And then we have one more. So the last one, example 3, we're going to look at is 3 over x squared plus 1. Again, we have an x in the denominator, so we could have a case where there was division by 0, which we have to exclude from the domain. But in this case, if we want to see when x squared plus 1 equals 0, to solve that, you get x squared equals -1, which we don't do imaginary numbers when we're graphing. So there's no solution to that. So that means that the domain is going to be x is real, right? X is going to work for everything here. That's it. Now, at this point especially, I know that you probably don't know how to graph this one. It's kind of a tricky one to graph. But if you do graph it, well, let's think. If the domain is all reals, is there going to be a discontinuity?
No.
No.
Yes.
Maybe.
There shouldn't be a removable, right? Well, there could be, I guess, if it's a piecewise function. There won't be an infinite, right?
No.
There could be a jump if it was really weird, but there's not. So yeah, pretty much you're going to be in good shape. But if we graph this, we have a point here at 0, 3, and then it kind of goes like that. Kind of looks like a bell curve, almost. Now, some different things we might think about on this. So as we look at this, that appears to be continuous, right?
Yes.
Every point's defined, so that's continuous. What would be the range?
Everything
It looks like everything, 3 is the high point, it looks like. Do you think this is ever going to cross the x-axis?
Yes.
Was this ever going to be negative or equal to 0? 3 divided by nothing will ever give us 0, right? So that's not going to happen.
No.
And is x squared plus 1 guaranteed to be positive?
No.
Yeah.
Yes.
I'll try it, but if you take a negative and square it, it becomes positive. If you add 1, it becomes more positive. So here the range would be y is contained from parentheses 0 to 3 bracket. Right, 3 does exist, but 0 is an endpoint that's never quite reached. You would use a calculator for that, obviously. That's not anything I expect to do right now. So we'll go ahead and stop there for the day.